Hello, and welcome to part 5 of this webinar series on model-based design for DO178C software development. My name is Mike Anthony, and I'm an application engineer with the MathWorks. This particular session, we're going to focus on verification of the model using formal methods. If you watched part 4, we talked about verification of the model against requirements, but the only verification that we used in that session was verification by simulation. This webinar is going to focus on other techniques for verification, specifically the use of formal analysis. And what we're going to see is we're going to start from where we left off in part 4. So at the end of part 4, we had successfully tested our model using our requirements-based test, shown that our model met our expected outputs for all of our requirements-based tests, and furthermore showed that those requirements-based tests also gave us 100% model coverage. So at the point that we're at right now, we should feel very comfortable that our model is complete and correct and consistent. However, now we're going to apply formal analysis. And the point of formal analysis really is to check kind of the robustness, if you will, of the model. So by running the requirements-based test, we've shown that for those specific test cases that we came up with, we're meeting our requirements. Formal analysis is one way to get at that question of how do we know that our model is going to satisfy our requirements for all possible test cases. And that's a very difficult problem to answer if you're only doing verification by simulation. So that's where formal analysis comes in. So if we jump into the tools, again, we're going to start with exactly the same model that we've been working with in all the other webinars. So let me open this up. And again, at this point, the model has already been tested. We've already verified it. It passed all of our requirements-based tests, and we got 100% model coverage. All right. So the key tool that enables verification through formal analysis within the MathWorks tools is Simulink Design Verifier. And Simulink Design Verifier really has three different aspects that we're going to make use of. All right. So the first is what we call design error detection. All right, and we'll look at what that means. The second is what we call property proving, and the third is automatic test vector generation. All right, and we'll discuss how all three of those features fit into a DO178C type workflow. All right. So the first one we're going to use is detecting design errors. So from our model, under analysis, we can go to the design verifier option, and I'm going to open up the options. You can see here in the menu, here's the three different capabilities: detect design errors, generate tests, prove properties. All right. I'm going to open up the options. We're going to start with this design error detection feature. All right. And this feature can really be used in two different ways. So if we open up the options, you can see that there's these two checks, checking for integer overflow and division by 0. We also can check for specified intermediate minimum and maximum values. So in the model, if we specify mins and maxes, we can use this particular feature to determine if it's mathematically possible for us to ever violate those min and maxes. And one of the newest features of this, so we can also look at the potential for indexing an array out of bounds. So if we're using mux signals, or say we have MATLAB function blocks in the model or something like that, we can look for the potential for out-of-bound array accesses. All right. So these four checks kind of work together, and then there's this dead logic detection. Okay, and so we'll do that second. So let's start with this, and we're just going to look at integer overflow. We're going to look for potential divide by zeros. I don't have any intermediate minimum and maximum values specified, so I'm not going to select this. And I'm not using any mux signals or array signals in this particular model, so I'm not going to select this either. All right. So I'm just going to look for integer overflows and divide by zeros. So if I hit OK, then I can come back up into my model and under Analysis, Design Verifier, detect design errors for this model. All right. And so what this is doing is behind the scenes we'll actually create an intermediate mathematical representation of the model and then run formal analysis on that intermediate representation. And behind the scenes, what this is actually using is the polyspace verification engine. So polyspace is designed to work on the C source code or C++ source code or even Ada source code. But behind that tool is a formal methods engine. And what this is doing is we're creating an intermediate representation of the model that we can then feed to that polyspace formal methods engine. And that's how behind the scenes we're actually doing this kind of analysis. So these errors that we're looking for, indexing arrays out of bounds, integer overflows, divide by zeros, these will sound familiar if you've ever used polyspace before. Okay, so once the analysis is completed, it's similar to model coverage. So you can see that we get both a report as well as some model coloring in order to indicate if there's any potential issues. All right, now I need to emphasize, remember that we already ran this model with all of our requirements-based tests, and everything passed, and we had 100% model coverage, right? And so that's kind of, I would say, a common stopping point for most people. At that point, they would say, I'm done with my model, I'm going to move on. So anything that we find using these techniques is something that likely represents the possibility of a latent error that we may never find at all, or if we're lucky, we might happen to find it, say, when we're doing our code testing. All right, so just keep that in mind, because it's most customer workflows don't make use of formal analysis. And so to me, it's very important to recognize that even in a model that we felt very comfortable with and was fully tested, it's still possible that there may be latent errors in there. And so that kind of emphasizes the importance of doing this kind of analysis. All right. So if we look at the model coloring, we can see that everything inside my stateflow chart, so that's green. If we look inside of there, things are green. So here's a variable that we're incrementing, and so as part of that incrementation, we're looking to see if there's any possibility that we could ever overflow this variable count. Clearly we can't, because it actually has a hard limit as part of the timer function, and it gets reset when we come in here. So there's no possibility that we could kind of continually increment this variable until we exceeded the maximum value of the data type. So that's basically what this is determining for us. But you can see that this cam angle calc atomic subsystem is red. And if we look inside of there, we'll see that this divide block is colored red. And if we click on it, we'll see some details. And we're getting an error, and it's saying that this is a divide by zero. So what this is telling us is that this divide block has a potential divide by zero. Now, we all know that divide by zeros are very, very dangerous, so we need to figure out why this is a possible divide by zero. And if we recall from what the functionality of this really is, what we're doing here is taking the difference between the centroid of the green ball in the image and the center of the field of view of the camera, and then we're dividing that difference by the total image width to give us basically a percentage distance away from the center of the field of view. And what this is telling us is that in this divide, it's theoretically possible or mathematically possible in this model that this signal could be a zero. So what we need to understand is that actually the case? Is it possible that this could actually be the value of zero? Therefore, this is a real potential divide by zero. And so if we trace this back up and we go back out, we'll see that this image width is actually an input to the logic controller component. All right? And if we remember from one of the previous webinars, we came in here and we specified a data type and a sample time and a dimension for this particular input signal. But we have not, as of yet, defined minimums and maximums. And if you recall from the second webinar in the series where we were going over requirements linking, I mentioned in that session that it would be a really good idea that if all of our root level imports and outports were linked to an interface control document, right, an ICD. And typically one of the key things that you would include in an ICD is expected ranges for each of these variables. And so if we had an ICD and we link this to an ICD, we should be able to then understand what we expect the possible ranges for these root level imports and outports to be, and we could document those in this minimum and maximum fields within the import block. Okay, so this is, as far as a divide by zero, what we need to understand is it actually possible for this input image width to be zero? All right. And if we refer back to the system level model that we looked at in the first webinar of the series, we know that this image width is actually an output from the image processing component. And what it is it's actually constant within the execution of the model, and it's the width of the image from the webcam in pixels. All right, and it's an input to this particular function because that makes this function reusable. So if we ever changed cameras and had different resolution or higher or smaller pixel width of the image, we wouldn't have to change this algorithm, okay? But we also know that that image width, it's actually never going to be 0, right? We're never going to get an image from the camera that's 0 pixels wide. That's not possible. So the reality is that this is indicating that there's a potential error here, but it's not actually a potential error if we think about the larger context of the system level model, right? And so again, this is the same kind of thinking that you would use if you were using polyspace on code. You have to put a lot of thought into at what level you do this analysis and whether potential errors that we're indicating are really errors, or if we added more context to the verification, if that error would go away. So for example, in this particular case, if we ran this design error detection on the image processing component and this logic controller component together, we wouldn't see this error because in the image processing component where we create this variable image width, it would identify that mathematically it's not possible for that variable to ever be 0. All right. But it's not necessarily a good idea to have to always rely on having all of that additional context, right? And so again, this is why when you write ICDs, you would do something like document what we know the possible range of this particular variable would be. All right. So the way we would do that is, I think, to make this model a little bit more self-contained and complete. So what we can do is actually come in here and document what we know the possible range of these variables could be. So for example, the image width, I'm using a webcam. The size of the picture coming out of the webcam is not dynamic. It's actually constant, and it's 320 pixels. So I can actually document that the min value of this is going to be 320, and the max value of this is going to be 320. All right. Now, while I'm at it, I also might as well go into my ball position and document this as well. So this one, again, if we know that the maximum size of the, or width of the image from the webcam is 320, then we know that that's also the max that the ball position could ever be. Then we also know that it could be 0, but again, having knowledge of what's going on in that image processing, we actually know that that algorithm will output a -1 if the ball is not in the field of view at all. And so the minimum of this is actually -1. So now that I've documented those, right, it's important to understand that that doesn't actually change anything. So for example, if I generated code, documenting those ranges wouldn't make any difference. You wouldn't see any difference in the generated code from those. You can set up Simulink to turn on diagnostics to say if we exceed those for some reason to throw an error. That's usually a good thing to do. However, if you do turn that diagnostic on, it can slow down your simulation quite a bit. So just be aware of that. But for the purposes of this, what I want to do is rerun my design error detection. So now that I've documented these, Simulink Design Verifier will actually take those min and maxes into account when it does this analysis. So if I run design error detection again, right, it'll redo the analysis with the understanding that image width is always going to be value 320, and the ball position is always going to be a value somewhere between -1 and 320. All right. Now, if we look at the results, you'll see that now this cam angle calc atomic subsystem is green. And if we look inside of here, you can see that this divide block is now green. Right? So it's no longer a divide by 0 because it's not possible for this image width to actually be 0. So now it's telling us that this design is safe with respect to overflows and divide by zeros. Now, of course, with that said, we have to take a step back and recognize what actually happened there. So Simulink Design Verifier did this analysis based on what we documented the range to be. If we make a mistake in this documentation, then that could potentially give us a false sense of security, if you will. Right? If I put in 320 here, and the reality is that we were working with a camera and the width of the image could vary anywhere from 0 to 640, right? But I documented this to be 320, the design error detection would tell us that we're safe, but in reality, we're not safe. There is a real potential divide by zero. So it's very important to be aware that we have to be very, very careful when we do actually document these ranges, because it is possible for us to put ourselves in a situation where a mistake in the documentation of these ranges could give us basically a false safe result if we start to do this kind of analysis. So just be aware of that if you start to include these. You have to make sure that they're correct. Okay, so that's that first couple checks as far as design error detection. So that was integer overflow, divide by zero. Again, we didn't have arrays, so indexing arrays out of bounds. So the other part of design error detection is dead logic detection. So again, if I come back in here and we look at the options again, you can see that there's this other option, dead logic. All right, and if I select this, you'll see the rest of these gray out. And the reason for that is that these are kind of two separate types of analysis. And so in general, you're either doing design error detection for dead logic, or you're doing design error detection for integer overflow, division by zero, intermediate min and max values, out of bound array access. Okay, so now we're going to concentrate on detecting dead logic. And this is a really, really good thing to do anytime that you have any state flow in your model. In the previous webinar, we were looking at model coverage, and so clearly this detecting dead logic is closely related to that idea of model coverage. So if there's dead logic in a model, you would think that there's also a very good chance that we would never have been able to achieve 100% coverage. And so one use case for this is if you're running your, say, requirements-based test like we did in part 4, and you're having trouble getting to 100% model coverage, you could try running this dead logic detection, and it will be able to tell you essentially if anything in the model is mathematically impossible to reach. The purpose of this is it will indicate if there's any logic or any logical paths that we've constructed in our model that there's absolutely no way that we could ever come up with a set of inputs to access, right? Now, clearly, if you run this and there's no dead logic and you're still having trouble getting 100% model coverage, that's a different scenario, and we'll actually talk about that. That just means that you're missing just that right test case to access the functionality you want. And we'll talk about how Design Verifier can help with that. But the first kind of the first check that you would want to do is say, is any of this actual dead logic? In other words, is anything in here theoretically or mathematically impossible to ever reach? Okay. And so again, to run this, we'll come back up to Analysis, Design Verifier, Detect Design Errors. And remember, since I set dead logic, so now it's looking for specifically for dead logic. And in this particular model, things are relatively simple. The logic is not extremely complex. So as this is running its analysis, what we're going to see is that in this particular model, there is no dead logic. And so again, we can make use of this model coloring. And so if you look at the model, you'll see that everything is green. And what that's telling us is that it is mathematically possible to access every logical path through this model. Right? That's a different question, remember, than can we actually come up with the test cases to do so. We'll get to that in a second. This is simply answering the question, is it mathematically possible? And again, since this model is relatively simple, it is. And so it's actually a little bit more interesting to, say, look at a model where this is not possible. So let me open up a different model. All right. And in this particular model, we actually have some dead logic. All right. And this looks very similar. So let's just run the analysis and allow the tool to actually tell us where the dead logic might be. All right. So again, Analysis, Design Verifier, Detect Design Errors. So the first thing you'll see is now we have 29 objectives. If you saw in the previous analysis, there was only 26 objectives. So there is some different logic in here. And you can see right away that it's detecting some dead logic. So we can look at the report, or again, we can look at this model coloring. And you can see that the model coloring is actually indicating that the dead logic exists in this saturation block that we have on the final output of the model. And if we open this up, you can see that I've set a saturation with an upper limit of 100 and a lower limit of minus 100. And if you remember what this algorithm is doing, right, it's putting out an angle command to a motor, and that motor is limited to plus or minus 90 degrees. And so this saturation is limiting to plus or minus 100 degrees. And if we remember from part 4 of the webinar series, when we had to actually make a correction to get our model to work properly, we put in this discrete time integrator block. And inside of this block, we set the saturation to be plus or minus 90. So effectively what I've constructed in this example is we're saturating this signal to plus or minus 90 here, right, which is the output of this cam angle calc atomic subsystem. And then downstream, we're saturating that again to plus or minus 100. What the dead logic detection is actually showing us is that it's impossible for us to ever come up with a test case where the input to this saturation block is being greater than the lower limit is false. And it's impossible for us to come into this block with a test case where the input is greater than or equal to the upper limit is true. All right. So in other words, what this is saying is there's no way that we could ever get an input into here that's greater than 100. There's no way that we could ever get an input into here that's less than minus 100. And so if you think about kind of the implementation of a saturation block in code, it would be a series of if-else-ifs or case statements. And what this is basically saying is there's two of those statements that you would never ever be able to cover because it's mathematically impossible to ever actually make the conditions to get into those branches true. All right. So this would be true dead logic. So again, I just added this block into our model. We don't need it because we already had the saturation. I just added it just to show an example of what this looks like if the Simulating Design Verifier is able to actually detect any dead logic. All right. So let's close this. Let's go back to a model that's not broken. All right. So at this point, now we have the model. We've run all of our requirements-based tests against the model. All of those test cases passed. Those test cases gave us 100% coverage of the model. We've also used this design error detection to show that there's no possible divide by zeros or overflows, and there's no dead logic in the model. So again, we should feel very, very confident at this point that our model is complete and correct. All right. So the next feature we're going to look at is, again, a feature of Simulating Design Verifier called property proving. And what property proving really gets at is, again, this robustness question. Okay, so in this example so far, we've come up with one set of test cases, right? And so for each, you imagine for each requirement, we had a test case. And when we passed that test case, we said we're satisfying that requirement. The reality is, all we've actually shown in that case is that for that one specific set of inputs, we're satisfying our requirement. That begs the question, well, how do we know that we're going to satisfy that requirement for every possible set of inputs that the algorithm could ever see? All right. And that's a very, very difficult problem to answer if you're just doing verification by simulation, right? The only way that you could actually answer that to completeness would be you would have to come up with every possible input scenario that this algorithm could ever see, execute all of those, and look at the output for all of those and make sure that it conforms to your expected behavior according to that requirement. Right? Even for a very simple model like this, there's no way that we have time to do that kind of testing. First of all, it's very, very difficult to actually come up with all of those test cases. And there's so many of them that trying to find enough time to actually execute them is impossible within any sort of realistic schedule for any kind of real project. All right. So property proving kind of goes at this problem in a completely different way. And what it says is if we can give that requirement, that desired behavior, some kind of mathematical meaning, then in some cases it's possible for us to do a closed form mathematical proof to essentially show that the mathematics of the algorithm that I've laid out in the model will always give us the mathematical behavior that we define the requirement with. All right? So that's what we've done here. And so you can see what I have in the model now is what I call a verification subsystem, okay? And if I look inside of here, I've defined a property proof, right? And we're just going to go through one example. So I've actually written one proof, and this one proof satisfies two of my requirements. So requirement 1.1.1 said the logic controller shall determine if the ball is in the camera's frame of view. 1.2.1 said while the ball is in the camera's field of view, the logic controller shall command the camera to rotate to keep the ball centered in the camera's field of view. All right. So the trick to this is how do I give those two textual statements mathematical meaning? All right. And so the way I've done that is I've used an input to the algorithm, ball position, right? And I know that if the ball position has a value greater than or equal to 0, that means that the ball is in the camera's field of view. All right. So now to test the algorithm, we have to say if the ball is in the field of view, right, then in order to satisfy the requirement, basically we have to be in this tracking state. And if we're in this tracking state, then the output of the state flow chart tracking should be true. Likewise, the output of the state flow chart in frame should also be true. All right. And so that's what I've modeled here. I've said if the ball is in the field of view and in frame is not true and tracking is not true, then I have failed this property. It takes a little bit of practice to kind of figure out how to model these because you're kind of modeling the inverse of the actual algorithm that you already laid out in Simulink. But once you kind of do this a little bit, it actually becomes pretty easy. All right. So now what I want to do is actually tell Design Verifier, okay, go ahead and prove this property. In other words, do a closed form proof to show if there's any possible scenario where the ball position is going to be greater than or equal to 0 and in frame and tracking are not true. So to start this, again, I'll go under Analysis, Design Verifier, and this time I'm going to do Prove Properties, okay? And we can look at the options real quick and just see kind of what options we have as far as property proving. So you do have some, and this is using formal methods, and we actually have a couple different strategies that you can use. Prove is by far the most robust. However, if you have a large model and you're having trouble getting this to converge, you can start with find violation or prove with violation detection. They tend to work a little bit better, but prove is absolutely the most robust. So I always try this first because if I can get this to answer, then that's really the best conclusion that I can possibly get. All right. So let me go ahead and start this. And we'll see that this time, as it processes our model, there will be one objective. And that one objective really is that proof case that I laid out. And so what this is doing is trying to see if it's possible to violate that proof case. All right. And interestingly, it says that there is. And again, we really need to think about this, right? We already had this model so that it was passing all of our requirements-based tests. We had a test case for requirement 1.1.1, right? We had a test case for requirement 1.2.1. We passed those test cases. We had 100% model coverage. How is there a potential error in this model? Why shouldn't we have seen that? And again, this is what property proving really gives you. It's this ability to look at all of these different scenarios, right? So what this is telling us is that, yes, we found in our requirements-based test cases, we found a scenario where we meet our requirement, right? But what this is telling us is there is actually a possibility, there is a scenario where we will fail that requirement. All right. And not only does it tell us that there is a scenario, but it tells us what that scenario is. All right. So part of this is you can have Simulink Design Verifier actually create a test harness model. All right. And in the test harness model, it'll populate this signal builder block with a counterexample. And so this counterexample is the one that will actually go through and violate the property. All right, so what we can do is actually execute this model, and we can go in and look and see how it's possible that this is violating our proof case. All right, and this is actually interesting, so we're going to actually go through and run this. So if I look in here, I want to be able to actually look at my state flow chart. Okay, because this is where requirement 1.1.1 and 1.2.1 are actually acting. So it's kind of all about these transitions in the state flow chart. So what I'm going to do is run this, and I'm going to use Stateflow's ability to animate the state flow chart to see if I can understand how it's possible that we're violating our property. All right, so let me press play. All right, so a couple of things happened, right? So first, if we look in the state flow model, we'll see that this counterexample that Design Verifier generated, it got us from the home state into the tracking state. And then essentially, and if we look again at the actual inputs, you can see the ball then goes to -1. So that means the ball is not in the field of view. And so in our algorithm, that means we transition from the tracking state to the waiting state. And so now we're in the waiting state and we're iterating in the waiting state. And then all of a sudden something happens. All right. And so the state flow debugger pops up and actually says, hey, you have a runtime error. Right. So this is kind of odd. So we need to figure out what's going on. And so if we read this, it says conflicting transitions. All right. And if we look, it'll say that we're in the waiting state. And what this is indicating is that at the same time step, the transition out of the waiting state to the home state, the condition being count greater than 29, right, is true. And on the very same time step, the condition to get me from the waiting state to the tracking state, so ball pause greater than 0, is also true. All right, so what the test case that Simulating Design Verifier found is if I'm in the waiting state and on the same time step that I would want to transition back to the home state, if the ball comes back into view, then it's also possible that I could transition into the tracking state. That's the situation that Simulating Design Verifier has found that violated our proof, okay? And the reason it violates the proof is because if you notice in stateflow, the transitions out of the states are numbered, all right? And what these numbers mean is this is the order in which stateflow is going to attempt to take these transitions, all right? And so what happens is, in this case, the transition from waiting to home is the first one, all right? And so what happens is the ball position, so the ball is in the field of view, but because we check this transition first, we're actually going to transition from the waiting state to the home state. And when we do that, the output of the state flow chart tracking goes false. All right. And if we remember our property proof, it said that if the ball pause is in the field of view, so this is now true, right? Then these both have to be true. But we're seeing an example where this tracking becomes false. And that's the violation of our proof. All right. So again, this is really subtle. And I would actually say that the chances you would ever find that particular test case by trying to come up with test cases by hand is pretty small. All right. Now, we should go ahead and let this continue to go. So even though the stateflow debugger flagged a runtime error, I'm going to say continue. And let me get the actual model back up here so we can see what happens. All right. So if I say continue, right, you can see it was a little fast, but it takes the transition to home. And then the next time step, because the ball is back in the field of view, it then transitions into the tracking state. But what that means is that for one time step, we were actually in violation of that property proof that we set up. Okay. So that's the example that this found. And I think this is particularly interesting because I built this model and I expected to have to kind of come up with a different model to show this finding an error when in fact when I ran property proving, this was a real error. I had no idea that I had my logic wrong and this was actually embedded in here. So this is a great example of why property proving is so valuable. All right. So now we've identified this error, we have to figure out how to fix it. All right. So I'm going to close this test harness model, and then we'll go back and actually look at our algorithm. All right, and we'll figure out how to actually fix this. All right. So again, remember what was happening here is we went into the waiting state, and then at the same time that we hit our counter greater than or equal to 29, ball position became greater than or equal to 0. Those two things happened at the same time. All right. And we, because of the way the logic is laid out, took the transition from waiting to home. In order to satisfy that property, we should have taken the transition from waiting back to tracking. Okay? So there's actually two different ways that we can fix this, and we're going to go through both of them. All right? So the first is we can just change the order in which we check these transitions. All right? And this is perfectly valid. It basically just says we're like when you're writing code, if you do if, else, right? you're relying on the fact that you're going to check things in a certain order to have that logic be correct. All right, and so we can also depend on the order here and get the correct answer. And the way we would do that is if I right click on this transition, I can come here to execution order, and then I can actually say I want to check the transition from the waiting state to the tracking state first. All right, so you can see that now we're going to check if ball position is greater than or equal to 0 first, and then we're going to check and see if count is greater than or equal to 29, and then we're going to increment our counter, okay? So what this would do, right, is in that situation where we're in the waiting state, and at the same time count was greater than or equal to 29 and ball pause was greater than or equal to 0, we would take the transition back into tracking first because we would check this transition first. All right, so this is what I would call relying on kind of the order of the logic in order to make sure that our algorithm is correct. And there's nothing wrong with that. It's just important to be aware that you are relying on the order that you're going to check the transitions. All right. Now, does this actually fix the problem? Well, we could run that one particular test case again and see what happens. Okay. But when you do property proving, if it finds a violation and gives you a counterexample, that doesn't mean that that's the only counterexample. That just means that that's the first counterexample that Simulating Design Verifier happened to find. All right. So rather than just test that one particular test case, what I'm going to do is rerun my property proving. And if it passes, then that indicates that we not only fixed that one counterexample, but there's no other counterexamples left. All right. So really, with Simulating Design Verifier, in the property proving, you have to keep running it until it tells you that everything is proven valid. All right, so let's start this again. So I'm going to prove my properties. Again, there will be one objective, which is that one property proof that we laid out. And you can see that this time it said proven valid. All right, and so we get a report, again, that same recurring theme of automatic report generation. Simulating Design Verifier puts out a report that tells us, exactly what assumptions that we used, what approximations it made, what our proof objective was, and then whether we were able to validate, basically prove that to be valid or find some kind of counterexample, right? So in this case, everything looks good, all right? So going back to our fix, again, this was one way that we could have fixed this particular problem, all right? There's another way, right? The other way to do this, so if we go back to the model the way it was, right? So you can see that now I'm checking this, the transition from waiting to home first again, all right? So the other way that you could fix this is you can make the logic basically order independent, okay? And so to make the logic order independent, we have to actually change the logic here, all right? So if we're going to check this transition first, right, then what do we need to do? Well, we need to say we can only take this transition if count is greater than or equal to 29 and ball pause is less than 0. All right. So by adding this extra condition, we're basically ensuring that even if we check this first, we're not going to take this and if the ball position is greater than 0. And so that means this transition condition will be false. So then we would check this one. This one will be true. And so then we would take the correct transition back into the tracking state. Okay. So again, to check and make sure that this fix is actually valid, what do we need to do? Well, we need to go back and we need to rerun our property proving again. So if we rerun property proving, again, this will find not only if that fixes that one test case, but if there's anything else that could violate that specific property. Okay, so again, it's still just the one objective, the same one property proof. All right. And so hopefully what this is going to show is that this is also proven valid, right? Which actually is exactly what it said. This one objective was satisfied. And again, we get the same report, and this report says that we were able to prove that one property case to be valid. So what this tells us is actually that either one of these fixes is perfectly fine. There's no difference. It's perfectly acceptable to address that issue in either of these ways. All right. Now, as designers, we have to think about if we have a preference, one of these or the other. So do we have a preference about whether we model our logic and state flow to be order dependent, or do we want to be a bit more rigorous and make it order independent, just in case, kind of thing. So again, functionally, it actually doesn't make any difference. I'm going to stick with this just because it gives us an interesting example to go forward with. All right. So now we have our model. Our model is satisfying all of our property proof. All right, so everything's good. But what do we need to do now to this model, right? Especially in this case. So we made a change to our model and we reran our property proof, but our property proof, remember, was only addressing two of our requirements, 1.1.1 and 1.2.1. We've made a change to the model. And anytime you make a change to the model, what do you need to do? You need to do your regression testing. All right, so we need to make sure that that changed, fixed what it was supposed to, and we effectively did that by rerunning property proving and getting that property to be valid. But part of regression testing is that we also need to make sure that the change we made didn't break anything else. So we need to make sure that in making that change, none of our other requirements-based tests are now going to be invalid. All right, so what we need to do here is actually go back to that Excel spreadsheet of test cases and our Simulink report generator report file and re-execute all of those test cases and make sure that with this change, we haven't broken anything and we still meet all of our test cases, everything's still passing, and we also need to make sure that we're still getting 100% model coverage. All right. So right now I'm rerunning all of those test cases. If we remember, there was 6 of them, right? So still 1 for each requirement. So we're going to run through and make sure that we're still getting the right answer for all 6 of those test cases. All right. Now, in reality, you could say that we actually need to go and write property proofs for every one of those, and that would be a good idea. However, because property proving is doing these kind of closed form mathematical proofs, not every requirement is suitable for a property proof. So for all the ones that it makes sense to do that, so any of them that have specifically to do with kind of logic or linear math, it's usually possible. But if you have requirements that are, say, performance requirements, like frequency domain performance requirements or something like that, it's going to be very, very difficult to write a property proof to show that. Right? So let's say you have a requirement that says my closed loop controller needs to have 60 dB of gain margin and 60 degrees of phase margin. That's not going to be something that you could easily write a property proof to show. That would be very, very difficult. All right. Okay, so we have the results from our test cases, and the first thing we're going to see is that our state flow chart is red again, right, using the model coverage coloring. So this is bad. This is an indication that something funky is going on. Remember, we already passed all these test cases. We had 100% model coverage before. We showed that in part 4 of the webinar series, all right? And if we look through here, we'll see that we are actually passing all of our test cases still. So if we scroll down to the bottom in our conclusions, we're passing the test because each of our 6 test cases is actually passing, okay? But if we look at the model coverage report, you'll see that we're no longer getting 100% coverage. All right, and if we go into the model and we look, sure enough, what we'll see is this condition that I changed where I added this and ball position less than 0, right? This creates extra logical paths, extra coverage conditions that we would need to satisfy. All right? In particular, we can see that this one gives us a bunch of extra coverage objectives related to MCDC coverage. All right, and so you can see that that's actually what's going on here, is that this particular transition is not giving us 100% MCDC coverage because we're not properly exercising the second condition here, ball position less than 0. All right. So now we're in this situation where we made a change to the model to fix our property proofs, but in doing so, right, now we don't have 100% model coverage anymore. And so now, again, we need to determine what's going on here. So we ran our requirements-based tests, we passed our tests, but we don't have 100% model coverage. So we have to ask ourselves, is this unintended functionality? Well, no, we put it in there so that we could prove our property. So it's definitely not unintended functionality. We need it. Are we missing a requirement? Well, no, we're not missing a requirement. Requirements 1.1.1 and 1.2.1 are the reason why we put this functionality in here in the first place. So we're definitely not missing a requirement. So actually what this is yet another example of we're missing a test case. So we have all the requirements that we need, but what we aren't doing correctly any longer is exercising the model in every possible way with our given requirements. All right. So what we're missing is an additional test case related to requirements 1.1.1 and 1.2.1. All right. So we need to come up with that test case. So if you watched part 4 of the webinar series, we were in the same situation, and in that example, we actually just came up with the test case by examination, essentially. But that's not always very possible. I mean, for a smallish model like this, a lot of the times you can get away with that. But for very complicated models, sometimes it's very, very difficult to come up with that missing test case by examination. So this is where the last feature of Simulink Design Verifier comes into play, which is automatic test vector generation. All right. So in this case, instead of us having to come up with this test case by inspection or by hand, we're going to use Simulink Design Verifier to automatically generate the test vector that we're missing. Okay. So we have this model. Again, we can run our test cases. We saw that we weren't getting 100% coverage. We're missing MCDC coverage on this particular transition. All right. So what I'm going to do is actually, I can tell Simulink Design Verifier, so we'll go back into the options. So I saved off my coverage information. So I basically saved off the coverage that I was getting when I was using my handwritten test cases. So what I'm going to do is tell Simulink Design Verifier, I need test cases for 100% MCDC coverage. Okay, and I'm going to feed it existing coverage data. All right, and so I can go find my coverage data. So I can go find the coverage data that I got from my handwritten test, which in this case is in this V&V folder. It's right here, model cov data. All right. So what this tells Simulink Design Verifier is, as it figures out what all the coverage objectives are, any of those objectives that I'm satisfying with this coverage data, it's going to ignore. And so that means it's just going to generate test vectors to get coverage of whatever objectives are remaining. Okay, and so we saw that what that's going to be is basically the MCDC coverage objectives related to that and ball position being less than 0. Okay, so let's actually run this and see what happens. All right, so I'm going to kick off my Design Verifier automatic test vector generation. So you can see that, we know there was more than 2 objectives in the whole model, but there's only 2 that we were missing based on the existing coverage data that we have. All right, so Simulink Design Verifier generates those tests for me. Right, and again, we can look at what those test cases are. Right, so it'll populate them. And actually, in this case, if we look, the test case it comes up with is exactly the same as the counterexample that the property proving came up with. And if you think about it, that actually makes a lot of sense. Okay, but again, you can imagine scenarios where that's not necessarily the case. There's definitely going to be scenarios where, regardless of property proving, maybe you're having logic that you're having trouble covering with handwritten tests, and so this would apply. All right, so now Simulink Design Verifier has given us this test case, but now we need to really talk about test cases again and understand what we really have here. All Design Verifier has given us is inputs, all right? And inputs alone are not sufficient for a test case, right? We saw before that for a test case, it needs to be a requirements-based test case, and part of a requirements-based test case is inputs and expected outputs, all right? So what we need to do is take these inputs and then go back to our Excel spreadsheet, right, and understand how that test case maps to those requirements, okay, and then based on the requirement, so forgetting about the model, just based on the requirement, we need to take the inputs that Simulink Design Verifier gave us, and we need to determine with our engineering understanding based on the requirement, what the expected outputs should be. All right, so you can see that I tagged this as a 7th test case, basically, and it's a second test case related to requirement 1.1.1. And these are the inputs that Simulink Design Verifier gave us. And then I had to read requirement 1.1.1, and based on that requirement and these inputs, determine that this is the expected output. Right? So now what do I need to do? So I have this extra test case, right? Well, now I need to run this test case against my model and see if the model gives us the same answers as our expected output, right? And then I also need to make sure that all of these test cases, again, give us 100% model coverage, right? So what I'll do is just basically use that same report generator template file, right? And I just made the change in my Excel spreadsheet, and I'll just rerun my batch job of tests again and look at the report and understand, did we still satisfy all of our requirements-based tests, all right? And in doing so, did we successfully achieve 100% model coverage? So you'll see that now there's 7 test cases instead of just 6. All right. And then if we look at my test report, and I'll just scroll down. So we actually, the second one is the new one that we wrote, this one. And you can see that it passed. All right. And if we scroll down to the bottom, you'll see that indeed all 7 of my test cases passed. All right. And again, we can look at coloring, or better, we'll look at the model coverage report, and we'll actually see that these 7 test cases also give us 100% MCDC coverage of the model. So now we're back in the situation where our requirements-based tests are giving us 100% model coverage, and our model is passing all of those requirements-based tests. All right, so again, this is the situation where we want to be. But recall, this is also the situation that we were in before we even started doing all of this formal analysis. And so in this particular situation, the formal analysis was actually very, very valuable because it found a legitimate latent error in my model that I needed to satisfy. All right, and again, in this case, to get back to having requirements-based tests give me 100% MCDC coverage, I had to write a new test case. And that's because I chose to fix the latent error that Design Verifier found with this additional logic. Recall that the other way that we chose to fix this was, instead of adding this logic here, just checking this transition first. If we had gone forward with that particular fix, we actually wouldn't have been missing any test cases. And when we reran our original test cases, they all would have passed, and we still would have gotten 100% model coverage. Okay, so I just used this example because it's a little more informative. And again, it's a good example of how to use automatic test vector generation in a DO178C workflow. Okay, and this is a really key point, right? Because we want to remember that in DO178C, right, test cases, for them to really matter at all, need to be requirements-based test cases, okay? And so anytime we automatically generate test cases based on the model, we obviously can't use those to then test the model, all right? So when we use Simulink Design Verifier's automatic test vector generation, it's really just a way to assist us in coming up with the requirements-based tests that we need for coverage, all right? But as we did in that example, it's very important to recognize that the Simulink Design Verifier gives us input scenarios. It's then up to us or our systems engineers or somebody with engineering knowledge to then look at those input scenarios, look at the textual requirements, and determine that for that scenario what the expected output should be based on the requirement. And only after you've done that kind of analysis could you consider that test case to then be a requirements-based test case and then have it suitable for use for verification against the model. All right. So that's a very important point. Automatic test vector generation is very powerful in these types of scenarios, but in the end, it does take engineering knowledge to take the outputs of that and turn them into legitimate requirements-based tests. All right. So that's it for part 5 of the webinar series. Again, in this particular webinar, what we looked at was verification through formal analysis. So we actually came up with a very interesting example where we had the model from part 4 of the webinar series that was passing all of our requirements-based tests, and those tests were giving us 100% coverage. And by using formal analysis, we actually found, despite the fact that we were passing our test cases and getting coverage, that there was a latent error in the model. We were able to use Simulink Design Verifier and formal analysis to find that latent error and then help us come up with a fix for that error, and in one scenario actually come up with some missing test cases that we needed to get back to achieving 100% coverage. All right. So now we're very, very comfortable with our model. Our model is complete and correct. We also have, after using formal analysis, a good sense of robustness. So our model is not just correct for a couple scenarios. We're confident that it's correct for all possible input scenarios. So at this point, we're actually ready to go and start looking at automatically generating code from this model. And so that's what we'll cover in part 6 of the webinar series. Thank you.